All right, so this is Mr. Holsey with H Squared, Sufficiently Understood Science, and today we're going to be talking about Bohr models. So just kind of a refresh, this is stemming from our discussions on atomic structure. So our current understanding of atomic structure is that protons and neutrons are located in the center of the atom in an area known as the nucleus. And those electrons orbit around the center of the atom. Now, once again, these electrons are not physical subparticles, they are negatively charged waves. And so they are a little bit different. That's why they don't have mass. All of our mass is going to be here in the nucleus. Okay, so but the question is, we're looking right here at an atom, and this atom happens to be carbon. So how do we know that this is the structure that we are looking at? How do we know that this is the structure of an atom? Well, we're going to take a look at the periodic tile. So we know right here, this is our atomic number, right? And down here, we have our atomic mass. So once again, that atomic number represents the number of protons and the number of protons, but it's also representative of the number of electrons. So atomic number, protons, and electrons. Okay, and our atomic mass is the mass of the nucleus, which is the protons plus neutrons. Now, when we look at that atomic mass, of course, we round it, and it's going to give us our average, and we subtract that to find the neutrons. But these two numbers are going to tell us what is the nucleus, essentially. We can figure out that there are 6 protons and 6 neutrons. And also, in this case, we'll have 6 electrons. So, how do we know what these elements will look like as far as their electron configuration? To do this, we need to know the number of valence electrons in each group. So the up and down columns right here, will tell us the number of valence electrons the atom has in its purest form. So we're not talking ions or anything like that, in its most pure form. Now, the intertransition metals, these guys right here and down here, we're not going to worry about those this year. They have a very strange electron configuration that gets into subshells and things like that, and it gets very confusing very quickly. In fact, most elements after 20 get a little bit confusing, so we're going to keep it pretty simple for this tutorial. So group 1 is going to have 1 valence electron. Group 2, 2 valence electrons. Group 13, or 3A, will have 3 valence electrons. Group 14, and I should go ahead and label this as 1A, this is 2A. Group 14, or 4A, will have 4. Group 15, or 5A, will have 5. Group 16, or 6A, will have 6. Group 17, or 7A, will have 7. Group 18, or 8A, will have 8, except for helium. I'm going to erase that because I did that very poorly. I'm actually going to use a highlighter here. Except for this one right here, helium. This one is going to have 2 valence electrons. It's going to have 2 valence electrons because it is in period 1. Okay, and period 1 can only hold so much energy. So each level can only hold a certain amount of energy. We have our nucleus in the center. Our first shell can hold a maximum of 2 electrons. Our second shell can hold a maximum of 8. I'm going to switch to purple. Our third shell can hold a maximum of 18, and our fourth a maximum of 32. Now, this is the valence electron beginning configurations for all atoms. what we're going to see in just a moment is that the atoms that we're going to work with are going to have a little bit of difference than what you're seeing right here. So how do we know how many shells there are for each element? Well, we have to look at the period number. So each row has a different number of rings. One ring, so the first row has one ring. The second row has two, 3, 4, 5, 6, 7. As you go down, these are your period numbers, okay? So these are your period numbers. And they simply tell us the number of electron shells for each horizontal row on the periodic table. And so if we're looking at carbon, it's going to give us some indications. So carbon is located right there. And so if we're counting our group numbers, we have 1, 2, 13, 14, 15, 16, 17, 18, and so it's in group 14 or 4A, so we know it's going to have 4 valence electrons. Let's check that. 1, 2, 3, 4, yep. And since it is in period 2, it should have 2 rings. 1, 2. So why are there different numbers of electrons in the different rings? The most important thing you need to remember when understanding why there are multiple shells and why they're not all just in one is that each ring can only hold a maximum amount of electrons as there are elements in that row. Okay? So that's a big little tip. Each ring can only hold a maximum amount of electrons as there are elements in that row. And it's really interesting that it aligns like that. And so each one can only hold so many. And that's because of the amount of energy that each row can contain. So period 1 can have a maximum amount of electrons of 2 because there are 1, 2 in that row. Ring 2 can hold 8, maximum amount of 8. Ring 3 can hold a maximum amount of 8. Now, I know exactly what you're thinking. Whoa, wait a minute. Didn't this guy just a few minutes ago say that the electron configuration was 2, 8, 18, 32? Yeah, I did, and that is a legit valence electron configuration. So don't get too crazy yet. Don't get your pitchforks and try to, get me quite yet. But there is a reason why I said this. So the problem here are the transition metals. These transition metals can have different valence electron configurations. So they don't have traditional valence electrons. And we're going to ignore them when we're drawing our Bohr models or Lewis dot diagrams, because essentially what's going to happen is because I said 2, 8, 18, 32. So what they will do is they'll go to 2, 8, and then 8, and then they'll start actually they'll fill in like 2 here, but then they'll start adding to a third row up till they get to 18. So we're not going to worry about those just yet. Just keep those out of your mind. So the valence electron configuration that we're going to use for this year is a lot simpler. And so that valence electron configuration that we're going to work with this year is going to be a lot more simple. 2, 8, 8, 18. And so this is the valence electron configuration that is going to work for the elements that we are working with this year. So don't worry about it. We will be good. All right, so we're going to take a look at the Bohr model for oxygen. So oxygen is in group 6A. Group 6A, or group 16, and it is in period 2. So what that tells us is that this element is going to have 6 electrons in its outermost shell, and will have two shells. And so let's take a look at that. So here we go. We have looking at our atomic number. Okay, 8 protons, and our atomic number also tells us the number of electrons. So in our first shell could hold 2, 1, 2. Our second shell could hold 8. We have 6 left. 1, 2, 3, 4, 5, 6. So there we go. And so we have our two of them. And so we're using 8-man to figure this out. So the current atomic structure is attributed to scientist Niels Bohr. Now, Bohr theorized that electron motion could not be predicted, but that we could determine where we could find them, and Bohr called these the electron clouds or electron shells. So there are 7 clouds, but we're only going to cover 4 because they can overlap, becoming far too advanced. And so each cloud is limited to how many electrons it can hold. Cloud number 1 can hold 2 electrons and only 2. Cloud number 2 can hold 8. Cloud number 3 can hold 8 or 18, and these, I'm going to put a T by this. This one, that's for transition metals. So we're going to focus on this. So 2, 8, 8. And cloud 4 can hold 18 or 32. And this 32, once again, is the transition metal. And so 2, 8, 8, 18. And so we're going to call this the 2, 8, 8, 18. That's going to be our simplified model. That's going to be our simplified valence electron configuration. So we're going to do a little bit of practice. So we know, if you ever want to just do this on like a worksheet or something like that, just write this out. 2, 8, 8, 18. Now, keep in mind, you'll only have 8 valence electrons in the outermost shell. That's as many as you can have. But if you had 7 electrons, we'd fill the first shell or cloud with 2, because it can only hold 2. Now, we still have 5 remaining, so we know there's going to be a second shell. 1, 2, 3, 4, 5. And so we can actually figure out what element that is, but we're going to go ahead and skip that for right now. So if the outermost cloud has not been completely filled, we're talking completely filled means it has 8 valence electrons, then the atom is considered to be reactive. Even if it has 7, if we remember, those halogens are really reactive. They have 7. But if the outermost cloud is completely filled, the atom or element is considered unreactive. They're not going to bond very well. So let's do a little bit of practice. So 4 steps. 4 steps in drawing a Bohr model. First, we determine the protons, neutrons, and electrons. Step 2, draw a nucleus about the size of a nickel. Okay? So just something about that big, because you're going to have to write protons and neutrons in there. So you need to have something big enough that you can write in. So you'll write the protons and neutrons inside the nucleus. 1, in this case I'm going to do 0. And start drawing and filling electrons with dots for electrons. Here, so I have my 1 electron because my protons and electrons are going to be equal, and this is going to be hydrogen actually. So I just drew a Bohr model of hydrogen. So let's see how I did that. So we're going to use pen. We can use 8-man as well. So let's practice with 8-man. So my atomic number is 1, which is equal to the number of protons and equal to the number of electrons. So my atomic mass is 1. My atomic number is 1. I subtract those. Gives me 0 neutrons. So 1, 1, 0. So I'm going to draw my middle part there. That's going to represent my nucleus. All right, that's going to represent my nucleus. And sometimes when I'm drawing these out, so I don't get confused on shells, every once in a while I'll do a little dash line to represent my nucleus. If so I don't mess up, and I'll go back in and fill it in. But it's up to you how you want to do that. So anyway, I've drawn my nucleus right there. And so I have 1 proton, 0 neutrons. I'm going to add my first shell, and I'm going to add my 1 electron. And so cloud 1 can hold 2 electrons. So this would be considered a reactive element. So let's try another. Now we have helium. So we're going to do our 8-man. So my atomic number is 2, means my proton 2, my electron 2. Man, my mass is 4, my atomic number is 2, which means I have 2 neutrons. So pen 2, 2, and 2. I'm going to draw my nucleus. 2 protons, 2 neutrons. I'm going to add my shell. 1 electron, 2 electron. So check, check, check. Now cloud 1 can hold 2 electrons. And so this is unreactive. And it makes sense because helium is one of the noble gases. Let's try another. So this time we're going to do nitrogen. So we're going to do 8-man. So my atomic number is 7. So my protons will be 7, my electrons will be 7. Man. My mass is 14. My atomic number is 7. We're going to subtract that. It's going to give me 7. So I should have 7, 7, 7. So I'm going to draw my nucleus right there. 7 protons, 7 neutrons. My first shell, 1, 2. So I can't put any more in there because the first shell can only hold 2 because there's only 2 elements in the first period. It can only, remember, that's a little rule of thumb. So now I'm going to add a second shell. So I know that I've already used 2 of them. So if you ever want to do this, like out to the side, like as you're making these, like start with 7, you've knocked out your first shell, I have 5 left. All right, that's always a good little trick. And so I'm going to start adding these in. There's the 5. So cloud 1 could only hold 2, but cloud 2 can hold 8 electrons. So if we only have 5, this would be a reactive element. Let's do another. Let's do neon. So ape. So 10, 10, 10. Man. 20, 10, 10. 10, 10, and 10. So I had 10. I got rid of 2. I had 8 left. I was able to put that in the second shell. I'm down to 0. And so now cloud 1 could hold 2. Cloud 2 could hold 8. That happens to be what's in there, and so this is unreactive. And this has been our tutorial on Bohr models. This has been Mr. Holsey with H Squared Sufficiently Understood Science. Remember to like, share, subscribe, hit the bell notification to know whenever we post a new tutorial. All right, catch you later.